Hey there. In this part of the PySpace lectures, I'm going to discuss the PySpace solution to the Navier-Stokes solution, or Navier-Stokes solution in physics. There's an awful lot of talk in physics about, in modern physics, about high-speed particles, hadron colliders, neutrinos, all that good stuff. But in what I would call classical or legacy physics, there's one or two pretty big unsolved mysteries in physics, and one of those mysteries in physics is the idea of turbulence. So, for example, if an airplane travels at high speed, one of the things that jet designers or plane designers have to cope with is turbulence due to the way that the air moves over a wing foil. If you run a tap fast, you'll see that the water frizzes up due to the fact that there's this turbulence that emerges at high velocity within the fluid. So air and water are essentially fluids. They're essentially the same thing with different viscosity. And we have in physics a attempted solution to it, I think back in the 1700s, by Navier and Stokes. So two different people came together in different locations, and in the physics that we know today, we have what's called the Navier-Stokes equation, and that is our best guess right now at how to model the flow of a liquid. So I'm going to go through how it currently works in physics and how you can how we treat those formulas in PySpace, and how we can model what's called turbulence in there, and explain how that fits into the overall design pattern. Now, in terms of actual, where does this fit into the PySpace theory? This is the blog up here, pyspace.blogspot, in my case .ie. If you were in .com, it would bring you to the same location. There's two sections I'm going to bring up today. There's the advanced formulas derivation section, and then there's what I call the quantum theory doctrine formulas. Now, the advanced formulas derivation I've talked about before, and in that there's discussions about how to model kinetic and potential energy, and we're going to build off how to model kinetic and potential energy, and we're going to move into the we're going to model that in a more general way in the quantum theory doctrine formulas, and then we're going to bring in the concepts, the Navier-Stokes concepts, which are kind of bundled in together to try and explain how it all works. So there's things like pressure and temperature and things like that. So if you're not sure what I'm talking about, or if you are, if you just go to so that's where it fits into the theory here in terms of the documentation. If you go to Wikipedia and you search for Navier-Stokes and you go to Wikipedia, the general solution that is in Wikipedia, and it's pretty good, is there's what's called the continuity equation, and it's just it's sort of a fancy name for basically saying that this one side of the equation, when added up with the other side of the equation, equals 0. In other words, all of the behaviors that you see of fluids, if you measure them in a certain way, add up to the other way of seeing the fluids. So let's just take a quick look at the formula here that's in the Wikipedia. There's the symbol here for density, which is a standard enough idea, the mass over volume idea for the fluid. It's your density. The V over T, which is the movement of the fluid. So that we're modeling the density and the movement of the fluid, and we're adding to that this slightly odd looking expression here. If you're a physicist or you're mathematically minded, this is no big deal, but the notation itself is very inelegant, and it is the product of a lot of people who worked on it in the 1700s. A lot of French physicists, Poisson and people like that. They came up with this this notation of derivatives and so on, and Gauss worked on it. But what this piece here is trying to say is this is what's called convective acceleration. And what it is it's our best guess at trying to predict how movement in a fluid creates turbulence in another part of the fluid. So what we're modeling here is the movement of the fluid, let's say the linear movement of the fluid with respect to time, and it has a certain density. And then there's this turbulence piece in fluids, which we don't really have a good handle on. It's one of the great mysteries. There's no great kind of unifying theory for how it all works. I am attempting to do that in PySpace. It's my best guess. I will talk about it further in other lectures. But the simplest example is if you're on a boat and the boat pulls off from the dock and you're at the back of the boat and you see the propellers churning up the water. One of the things that you'll notice is that as the boat pulls away and the water moves around the boat, it not only moves behind the boat, it swirls. It has these circular eddies or swirls which are turbulence based. And if you look at weather patterns on the Earth, you'll see they swirl in these shapes, these circular shapes, and they're similar in nature to magnetic fields in that they're due to non-charged mass. So I'll talk later about how I model that in PySpace, but that's essentially what this part of the formula is talking about. We move over here to this part of the formula. We talk about pressure next. So we all know air pressure. You know, you're on a plane and the plane descends and you have to move your jawline in order to adjust air pressure. So PySpace models pressure as well, and then we have the concept of temperature here, the change in temperature, which again we all know it's pretty intuitive, and so we can you know, if we boil water, for example, we know that it produces steam, it becomes more kinetic. You know, it's how we power engines and so on. And then over here we have this what's called the kind of the external forces part of the equation, and that's essentially the, say, gravitational potential. So that would be like if you have water in a tube and you want to model that in terms of the overall equation. So what we're saying here is we add up all these forces on this side of the equation, and they will match the resulting behavior on this side. So what we have here is what I call the local plane. We have particles of a liquid, or either air or, say, water for the sake of argument, and they have pressure, they have temperature, and they're inside some kind of a gravity field potential. And then on the left you'll see some kind of movement with respect to the observer. The liquid will have a certain density, and there will be, if the liquid is moving fast enough, you will see it swirling or creating eddies or vortices. So mostly in physics, moving down here now, mostly in physics, physics has to solve particularly problems, and the way they do it typically is they have these vector lines at fixed points in liquids, and then they have them going up and down, and they basically don't try to model an individual particle moving. They try and model an individual point and say how the point will move, and from that you can then you get the idea of a moving liquid. So there's two approaches. There's this one where you model the the points and then the vectors, and then there's another way of modeling it where you kind of have streamlines and you try to follow the streamline, which is more complex, because if you don't have a good theory for how turbulence works, well then it's pretty difficult to do it correctly. So what we have right now in physics is our best guess. So I'm going to move back here. So basically that's the classical approach to liquids or air. A great example of how we haven't solved it correctly would be if you're a gamer, or let's say you play Crisis and you go into the water. You'll notice when you go into the water as a gamer, the water on the surface always looks correct. It sort of has the up and down motion, but there's no eddies in there, there's no swirling behavior. Computers can't model it correctly. There are high-end systems that do this, in high-end systems for various groups that need that level of detail, but even they would use kind of best guess algorithms. So let's now that we know what the Navier-Stokes is talking about, which is the movement of a fluid with respect to time, having these turbulence fields, having specific density, and being subject to pressure, temperature, and external forces such as gravity, gravitational potential. How do we model that in pi space, right? I mean, it's all good and well me telling you what we don't know. So how can pi space help somebody model that complex problem? So we move on to the next part of the theory, which in pi space now. We're switching over to pi space. In pi space, this is the official website, pi space theory storytwig.com. There is what's called the advanced pi space formulas document. There's a HTML version and there's a PDF and their equivalent, and in there I derive the two core relationships in physics that we all know and that Newton built all his work from, and I did something similar in pi space, and that is the relationship between a kinetic energy and a potential energy. Now in the Newtonian world, a kinetic energy is half mv squared. It's pretty straightforward. It's the average velocity times the velocity, giving you the sum of the velocities for some kind of an acceleration, for example, into gravity. Now in pi space, I'm not going to derive this here. If you just read the doc, but the basic idea of pi space is that I model reality based on spheres, and in pi space, if you move, your sphere shrinks. So what comes out of that is this formula, which is m times 1 minus the cos of arc sine v over c. If you want to get back to Newtonian units, you have to, if you're in Einstein units, you divide v by c, and then you multiply the solution by c squared, and you get back to Newtonian units, and the answer is pretty much the same. If you're not sure about what I'm talking about, you can take a look at this document. It's called the Advanced Formulas PDF. Now, later in the document, I then show that the area gain is equal to the area loss. I'm just going down to the kinetic energy version. So so what we can do in Newtonian, the Newtonian work, is we can map the gravitational potential to the kinetic energy. The two mass, the mass on either side cancels, and then we're left with a simple kind of continuity type equation where potential energy is equal to kinetic energy. Pretty straightforward. You can work with these examples in the document if you're interested, if you're not sure what I'm talking about. But that's basically potential energy is kinetic energy. Area gain of a sphere is equal to the area loss of a sphere. That's fine. Now, the Navier-Stokes is a really fantastic. It's really one of the more fun. It's something that Newton never dealt with. Newton did not solve Navier-Stokes. He did kinetic and potential energy and all that good stuff, and he did not do Navier-Stokes. A new branch of mathematics, field theory mathematics, was created by people like Gauss and Navier and people like Stokes, who used these operators, the del operators, and they used these other operators which were non-Newtonian. So what you have in physics is this French version of physics and almost an Anglo-Saxon version of physics, which is this is the Anglo-Saxon version here, and then you move over to to the other version of physics, which is the I'll show you what I mean by that. This would be this symbol here, for example, the V dot del V. If you're doing electronics, if you're a physicist and you do electronics, you know the meanings of these things, the del operators and so on, and they're kind of like they're kind of differentiation and integration operators. So this is what I call, now it's just my own interpretation, the French version of physics. And this stuff is really powerful, but the notation's obscure. So there's the del operators, and these are the changes. I just don't like the operators, but they really do work, right? So in PySpace, what I've done is I've created the same notation to represent these operators. What I'm trying to say is I've created mathematics that represents both the Anglo-Saxon style operators, such as these ones. Say actually the half mv squared equals g times h is a half mv squared, the Newtonian, which is sort of the Anglo-Saxon way of doing it, I think, and that's just my own interpretation. And then you have Navier-Stokes using these del operators, which originate, as far as I could see when I studied it, from kind of France and whatever. But these operators work, and this is how you just do it if you want to add up electric currents and fields. You use these operators. It's essentially another way of representing integration differentiation. Now in the PySpace theory, integration is just the addition of the area change due to a sphere, and differentiation is the rate of change of area change to that sphere. Now I'm currently in the quantum theory PDF here, in case you're wondering. This is the quantum theory PDF. So I can't cover everything in one podcast. It's just in one video. It's just not possible. So I just want to give you a heads up on what the document contains. At the very beginning of this document, it talks about the exponent, and it talks about Schrödinger and how you can combine two different waves orthogonally to produce the probability of something appearing at a point. But it moves into, later in the document, from about 127 onwards, it moves into the idea of the more classical Navier-Stokes stuff. Now liquids and fluids are very complicated to model, and there's a variety of people who've solved it in different ways. So what I have attempted to do in this document is just to show how all of the different approaches that have been used to do it have been done, and how to map them to PySpace. And at the very end of the document, I describe the final approach to how to do Navier-Stokes and the turbulence and so on. So there's the Reynolds number. So what that is this, it's the spread of what I call the non-local wave function, right? So in PySpace, what I do is I create now I've discussed this in other documents. So if you're not sure what I'm talking about, you're just going to have to either read the doc, or you're going to have to look at the earlier bits, read this doc, or watch other videos. But basically what I do is I've created a Hamiltonian. Now the idea of a Hamiltonian is essentially it's just a continuity equation where you have on one side of it you have addition of area change and you then subtraction of area change, and basically they both equal zero. In other words, energy is, you know, it's that thing that physicists are always going about. Energy must be conserved. In other words, the way I explain that in physics in my stuff is the gain in area is equal to the loss in area. So I have these formulas here where I have this would be the kinetic component. I bring in a wave function similar to the Schrodinger stuff. I have this is the kinetic component, and this is the gravitational component. So that's a gain and that's a loss because you're moving. So if you're not sure, this is just a quantum style notation for a wave function. I mean, that's just your wave function. In the advanced sections, I kind of flesh out these wave functions a little bit better. But just think of a wave function getting shorter and longer, and certain effects make it longer or shorter. In this case, it's kinetic energy, and then this is the base wave function, which is the relativistic component, and then this is the gravitational potential, making it larger if you move up by height h. Real simple. Now, we take Reynolds number in the document and we describe that. I won't go into too much detail, but I apply Reynolds function here. And then what I do is, I do something I think is pretty nice. And what I do is, in the same way that in the Navier-Stokes, they have the turbulence and the velocity, and then they have pressure and temperature and then this gravitational force on the other side. They have it broken out in sort of like two different sections. And the way I do this in the quantum theory doc is I talk about what's called the local plane, and I talk about what's called the non-local plane. And it's pretty simple. The mathematics actually aren't that complicated. You have what I call the local plane, and what the local plane is it's our reality. It's sitting in a room under gravity, under air pressure. The sun is shining. There's a certain amount of temperature, and maybe there's a bit of a breeze, and there's a few eddies in the room, wind eddies. So what I do is I say there's a local plane, which is this area here, and this is a Hamiltonian, and then I say there's another one over here which I call non-local, and this is the gravitational potential. So what I say is there's gravity here, there's a kinetic component due to gravity, there's pressure here, and then there's a kinetic component due to pressure, right? So they're both that's basically saying, and that's saying that's local. In other words, that's like in your room, and this is non-local. So this is the whole planet, right? Due to mass, yeah. So that's fine. I explain later in the document, I won't go into too much detail, how the Reynolds number is just about how the wave function is suppressed due to viscosity, right? I won't go into it in too much detail. I talk about lift and drag. I won't go into that in too much detail here. It's in the document. Then I talk about Pascal's law. This is a pretty important law. I show how with these formulas you can model Pascal's law, and you can show how the pressure can be manipulated based on the shapes of objects. So you can show, this is the hydraulic idea, where you can push a small amount of force through a liquid and you can magnify the force. Then I talk about the big kahuna of fluids. I talk about Bernoulli, which is real important, and the whole Bernoulli piece is so confused, because people just do not get why something that moves fast has low pressure. People just don't get it. They just don't. I mean, someone can teach you how it works, but nobody really finds it intuitive. The way it works in pi space, I'm hoping it's intuitive, which is that if you have high pressure and you move it through a lower point, there's lower pressure. The reason is it's the wave functions are being altered, and they in turn alter the size of the particle. So the wave functions are in here. So we talk in terms of wave functions. We model them with these formulas. I won't go into it in too much detail here, but basically Bernoulli's covered It's very fundamental, and I talk about the reason for movement of a particle in a particular direction. This is the principle of least action. Richard Feynman went on about it at great length. He understood the core importance of this. I have the rule for why something moves towards a particular direction. It's fundamental because it's why plane wings lift, and the tip of the plane wing in the theory moves in a particular direction, and so in the document I explained that if a plane wing creates low pressure at a certain point, and the wing moves towards it, and I show formulas for that, and that's fine. And then we move on to airflow around the ball. In the States, I know baseball is a huge sport, and there's a great amount of work done on getting the ball to spin towards the bats person, trying to outmaneuver them, and if the spin creates pressure points, and then the ball will move in that direction. That's how you get curved balls. So I talk about that, but the basic idea is it's manipulating. It's all about manipulating a liquid or a fluid to move and have an object in it to move in a certain way in that flow. I have some small words on how I think one could build an effective lift system. I have a more efficient way to do this in later videos, but that's for later. But basically, I explained the Venturi Effect and why it could work, and it's just basically if things move fast, they get smaller, and then solid objects move up towards them. I have a small video which is, to be honest, a little bit amateurish, but it demonstrates the principle. It's at the time of writing, it's a hairdryer blowing over a book on a weighing scales, and the book gets lighter because it lifts towards it. It's just a very simple. The point is to try and explain that you don't need aerodynamics in order to make something to work. The shape of it could be a book, a flat book. Anyway, I move on to the Lagrangian. This is where we get into the French physics and the way the French, describe a Hamiltonian. The Hamiltonian's more the Anglo-Saxon way. The Lagrangian's the French way. Same difference. It's a combination of kinetic potential, and then what I do is I start getting into Navier-Stokes. The other pieces are a build-up to what was there. I talk about the flux of a gravity field, and then we're talking about the divergence theorem and the gradient, and we're talking about Gauss, which is another way to represent gravity. And this is a gotcha even for physics professors. You can derive the Newtonian equations. You can describe the Newtonian equations for gravity using Gauss. And what catches a lot of physics professors is that they don't find 4 pi. So the Newtonian work hides the constant pi, whereas the Navier-Stokes, the Laplace and the Gauss stuff, it does have it, and then you get a lot of students asking, where did pi go? And the thing is that the problem with the Newtonian work is, and the reason why Einstein needed to bring in relativity was because Newton never brought in the concept of compression and decompression. He never built it into any of the formulas. He never modeled a sphere, and he never modeled it getting bigger or smaller. And for that reason, he let earlier in the last century, Einstein, with the work of Lorentz, came up with these transformations, which essentially I've shown in my documentation are just about the altering sphere sizes. If you don't know what I'm talking about, just look up my work and my introductory section on PySpace. So it all fits. So it's pretty straightforward. So then I move on to Gauss and Poisson, and then the Laplace operator, and then this is the thing I was talking to you about 4 pi, because it's about the sphere. Excuse me. And then I calculate the wave and the function, the wave and the function. And then we get onto the kind of the cooler stuff, which is convective acceleration, advection. Now, a lot of the terminology in this section is quite confused. Some people use it in different ways, and the reason is there's not a very good understanding of it, and people call it different things. Nobody has really nailed it, I don't think. But basically, we get into the Navier-Stokes equation, and then we do this formula that I showed you earlier. And what I do is I put all of the forces, pressure, temperature, and the gravitational force, pressure and temperature onto the same plane. So I'll just move further down here. So this is where I discuss the Navier-Stokes equations, and I derive what would be called the convective advective acceleration. So I'm not going to go into it in a huge amount of detail, but basically this is where I do convective advective acceleration. Then I do stress in a fluid, and this is called shearing in classical fluids. This is to do with viscosity and the way that it affects the area change due to velocity. And then I do heat. Heat's fairly important. Now, heat is actually one of the really cool things that you can manipulate. It's something within our control within this reality. And in later sections, in the superconductivity section, I'll show how heat alters what I call the local wave function. In terms of a fluid, we know that we can make it hotter or colder, and its physical properties change. But if you supercool matter, it behaves differently, and I show in a more precise way in the superconductivity section what that's about. But a lot of that understanding is built off these formulas and how they fit in with kind of fluids. So what I do is I lump temperature in with pressure, yeah, and so I put it into that Hamiltonian there. And then later we have the continuity equation, which is gravity and pressure and velocity. And then it's starting to look a little bit like Navier-Stokes. I explain that, and then I show how velocity is altered by pressure, how things speed up. People just don't get it. You put something into a more narrow tube and it speeds up. People don't get it, and the reason is the particle gets smaller relativistically according to this theory, and then it just speeds up. That is described here. Then there's the Pitot Tube. This is used in airplanes. A lot of unfortunate airplane accidents have happened because Pitot tubes get frozen. They use air pressure as a way to determine velocity. And then there's the Venturi, which is a similar kind of device for planes as well. And then I described that. I have some pretty nice stuff there. And then near the end of the doc, nearly finished now, I talk about Navier-Stokes for momentum and energy. And here I bring it all together. And this is the thing about the Navier-Stokes equation. It seems just like one equation, but it's really it's actually, if you can solve Navier-Stokes, if you can model it, you pretty much are almost there in terms of the classical world. You can pretty much model everything. So there is a kind of a prize for figuring this out. But it's actually very deceptive in that it appears that what all they're asking you to do is just solve like this equation and model turbulence. But really what they're asking you to do is to solve everything, right? So as you can see, all the stuff I had to do in order to get to understand and model this, there were so many dependencies. So basically you got the local and the non-local, you got pressure over here, and then you got temperature. You got to add your temperature. You got to add your viscosity. Yeah. Then you got to do your total energy change, excluding turbulence factor. And then the way turbulence is modeled in pi space is it's modeled in the same way as a magnetic field. It is a field due to movement relative to an observer. So so it has to be modeled on a different plane. But so what I do is I model the XY area energy with all the components that go in. I model viscosity. I model kinetic, relativistic kinetic. I model pressure. I model gravity, and I model temperature. So, and then and then you have to model. This guy here, and this guy here is really quite tricky, because in the Wikipedia Navier-Stokes, they're part of the same expression. You see the way they're on the same plane, but in reality, when turbulence occurs, it happens in another plane, similar to a magnetic field. It's perpendicular and circular relative to, the right hand rule. It moves perpendicular and circular relative to the motion. So the way that's done in pi space is we create a circular motion in the YZ for that plane, and it's again just based on these components, and then I solve. The nice thing about the pi space formulas is you can convert velocity to energy and energy to velocity pretty straightforward. And this is one of the huge problems with the Navier-Stokes equations, is you have these partial differential equations. They're absolute nightmare, and you can't really solve for them. With the pi space functions you can solve for velocity pretty simple, and this is what I do here. And it's really simple because you're using trig functions. You can use their inverse functions, and that's what I do here. I won't go into it in too much detail. So I can solve for turbulence velocity and flow velocity, and then I say adding external turbulence, and then I have a pretty important rule here in the document, and it's called the field comes first. Now, you might say, what the heck does that mean? And what it means is that if you are modeling a large system in real time, the field effect is the containing effect. So you got to model that first, and you got to sum that all up, and then you model the individual particle. The particle exists inside this field, which is the sum of a lot of waves that are being perturbed. So that's what I mean by this. I discussed that, and that's it. And that's how I model the Navier-Stokes. It is I thought it was going to be. I went in like a Boy Scout thinking this was just going to be some formula to reverse engineer. It is a monster. It is just a monster. It's the Godzilla function of physics. I had to reverse engineer so much. I've done my best attempt to describe it in a logical fashion in the quantum theory doc. The name might be a bit misleading. Maybe I should call the document Quantum Theory and Turbulence or something, or Quantum Theory and Navier-Stokes. And the reason is that I built the Navier-Stokes functions from quantum functions. So the idea is to have one function to represent everything, which is kind of the holy grail of physics. I'm not saying that this is the final solution, but I'm hoping it is a good pointer to someone who maybe is a qualified physicist who maybe could clean it up or whatever. I think what I've done is pretty logical and makes sense, and that's the Navier-Stokes in physics, represented in the pi space theory. Hopefully that was clear. The best thing to do if this interests you, maybe it doesn't, or if it does, the document is there. You can take a look, see what you think. Thanks very much.